And hi everyone, I'm Sherry. I'll be talking about UniPi, learning universal policies via text-guided video generation today. So the goal of this work is to continue pursuing the idea of generalist agent. And the reason that we wanted to learn generalist agent is so that the agent can generalize across environments and tasks, because we don't want to train an agent in a new environment every time a new environment comes up. And examples of generalist agents, including Gato and multi-game decision transformers and various other works that tries to learn a single policy across tasks and environments. And one of the challenges for learning generalist agent is the diversity of the environments, meaning that different environments have different state and action spaces. Another challenge is that different environments have a different notion of a reward. And the previous solution to overcome environment diversity is to either only learn environments that have the same action space, like multi-game decision transformers, or to utilize tokenization so that to convert all of the observations into a unified tokenized space. But this tokenization scheme might not preserve any knowledge from these large pre-trained models, right? Video models or text models, because it requires a lot of new data to be collected from the environments to be able to learn policies on top of these tokenized observations. And the previous solution to the reward diversity challenge is to use text as a reward to unify the notion of task success, which has been quite successful across different environments. And our solution to these challenges is to maintain the text as task solution to overcome the reward diversity, but use videos as policies so that different environments share their observations in the same video space, essentially the pixels. And specifically, if we pre-train on a large, diverse set of videos, including simulated robotic manipulation, real robotic manipulation, and even human videos, we're hoping that by pre-training on these diverse set of videos, we might be able to learn policies that can generalize combinatorially to long horizon planning tasks, to different set of multitask generalization, and also maybe the learned policies will be able to leverage these internet scale knowledge, such as how a human might cut a pineapple. And more specifically, how we use these video models to learn control policies is there are a few modifications that we have to make. First, usually for generative media, maybe unconditional or only conditioning on text is enough. But for control and these reinforcement learning tasks, we want to be able to condition on the current observation. So first, we have to do first frame conditioning. And second, for a lot of these videos, the background are usually fixed. So we want to make sure that generative videos have consistency across time, and which we conduct by replicating the first frame and putting the replicated frames as inputs to the conditional model. And next, we noticed that the temporal super resolution of these text-to-video models actually nicely aligns with the goal of hierarchical planning. So essentially, we subsample the frames at a coarser time frame and filling in the gaps in the middle. And this essentially maps to learning the key point of the plan and then filling in the details of the plan. And last, after we have the video, we need to recover these inverse actions to be able to execute them on the robot. But notice that we've kind of lifted the learning of a policy to the video level, which we have a lot of data from both humans and simulated and real robots to train. And then recovering the inverse dynamics is essentially looking at two images and compute the delta and saying what has changed. And that part is very easy once we have a very good video model and requires very few parameters. And to illustrate the capabilities of UniPi, we constructed this synthetic task where the language is to instruct the robot arm to color the blocks and then put the colored blocks in relation to some other blocks. And this is considered somewhat longer horizon because the robot has to know which color to dip the original white block into before placing it next to some other block. And we see that UniPi is able to generalize to new colors and combinations of these tasks. And we compare to baselines, which includes these behavioral cloning methods, which don't do any long horizon planning, right? We're generating all the videos of the future, whereas behavioral cloning is just doing the immediate next action, which kind of fails miserably for these longer horizon tasks that require planning and reasoning. And we also compare to approaches that does do planning, but without using videos. And without using videos, plants themselves don't really capture the external world, like where the blocks are, where the color balls are, right? So it's not a part of the robot state. And we noticed that UniPi is able to generalize a lot better than the other approaches. And next, we show results on the multitask transfer. These are a set of held out tasks that was not seen during training. And UniPi is again successfully generalizing to these new tasks. And also in terms of quantitative metrics. And then we show by pre-training on large internet scale videos and fine-tuning on these robotic videos, UniPi is able to perform these held out instructions on these held out initial frames to be able to generate these videos that actually complete the task in real world. And we noticed that pre-training, like fine-tuning from large pre-trained video checkpoint is actually important for UniPi to generalize, right? If we just train the video model from scratch, the generated video is likely to perform the task that was initially associated with this initial image, which is to grab this pepper. And whereas if we use the pre-trained checkpoint and fine-tune from there, it's actually conducting the right task, which is to put the carrot on the burner. And then quantitatively, we also show that using pre-trained checkpoint improves clip score, FID, and FVD, and it also improves task success rate after we've trained a task prediction classifier. So, and lastly, we show that all the components of UniPi is important for its good performance, including frame conditioning, frame consistency, and temporal hierarchy.